Hi, everybody. Welcome back, right, to our graduate statistics course. That's our week 11. And in this week, we're discussing the chi-square test. And we started with the chi-square test for goodness of fit when we're just looking at differences in the distribution of one variable in the population at large and in a particular data set. And now we're looking at whether there is independence between two variables. In this case, the death sentence and race. And the problem that we have is that we had a data set of 80, including 825 court cases, and we tabulated these cases in this contingency table based on whether or not a person got the death sentence and also whether or not they were white. Based on this table, based on the law of multiplication, we computed the expected probabilities of an individual getting the death sentence and being non-white, not getting the death sentence and being non-white, the probability of getting the death sentence and being white, and the probability of not getting the death sentence and being white. Okay? In blue, we have the expected under the assumption of independence, because the multiplication law only works under the assumption of independence. So we know what the counts would be if no relationship exists between the race you have and whether or not you get a death sentence once you're being judged. In black, we have the actual counts. So even in the case of independence, because human data is messy, you would not expect a perfect match. So now we need to know whether these deviations that we are seeing that are biased against black individuals, because not black, just non-white actually, and other races, I should say, because we shouldn't be using white as reference, right? So we should really here say individuals from other races. Then we have here that the expected number of black individuals that should have gotten the death sentence if race has nothing to do with that decision about the sentence should have been 22, and 33 got the sentence. So it's more people getting the sentence than would be expected if death, sentence, and race were independent. And the opposite is true for the white folks. So are these deviations large enough for us to conclude that really there is a bias there? Are these deviations, what's the likelihood of us seeing these deviations under the assumption of independence? So that's where we are. We need to compute that. And the formula is the same as before, right? We compute observed minus expected, we square it, and we divide by the expected, and we do the same for each one of the cells. We sum all of it, and after we sum, we have the chi-square statistic that we get, that we need to go to the right chi-square distribution to compute the probability of seeing that under the assumption of independence. So what are the conditions to running this test? Each case only contributes to one cell, which is true. Like each person cannot be in two of these cells, right? And each particular scenario, each cell, must have at least 5 expected cases. And again, we do have more than 5 expected cases in each one of the cells, so we're good. Then we need to identify the correct chi-square distribution, because that depends on degrees of freedom. In this case, degrees of freedom is the number of rows minus 1 and the number of columns minus 1. So here, let's look. We have, 2 columns. So we have 2 categories for death sentence. We do minus 1, that's 1. And we have 2 rows because we have only 2 race categories. So that's 2 minus 1 is also 1. So in this case, we'll need a distribution, a chi-square distribution with 1 degree of freedom, because 2 minus 1 is 1 times 2 minus 1, that's also 1. 1 times 1, 1. All right. Once we get that, we can obtain the probability of the estimated deviation or the calculated chi-square statistic under the null hypothesis. So if we pick a distribution with 1 degree of freedom, what is the probability of observing that particular value of chi-square or larger? If the probability is very, very small under the assumption that the two things are independent, in this case, race and the decision for the death sentence, if these two things are independent and the probability of observing that deviation is very, very small, then we dismiss the null hypothesis. So let's work on this together. Again, let's recap the hypothesis. Age old, nothing is going on. Race and death sentence are independent. The rate of death sentence does not vary by race. And the alternative hypothesis is that something is going on, that something is a relationship between the death sentence and race. They are dependent. The rate of death sentence varies by race. So same calculation, right? 32 minus 22 divided by 22. And then the same thing here. 251 minus 261 squared divided by observed. Same thing here. 33 minus 43 squared divided by 43. Same thing here. Again, you won't have to do these calculations in R because we have a cool chi-square test function that, just like the t-test, you won't have to do anything by hand, but I wanted you to understand where these things are coming from, right? So the deviation would be 8.41, okay? And the number of degrees of freedom, as I said before, is 1 because that's the number of columns minus 1 times the number of rows minus 1. So then we compute the p-value, which for a chi-square test doesn't change the interpretation, is the tail area above the calculated test statistic. And because the test statistic is always positive, and a higher test statistic means a higher deviation from the null. So we have here, what's the probability of getting 8.41 or greater, and the probability is 0.003. That's less than 0.05, so we reject the null hypothesis, right? So here's the probability of getting this test statistic or greater because we're setting lower tail to false, and we want the 1 degree of freedom distribution. Now, I'm doing this in a way that requires that you compute the deviation, but when we go to the lab, you'll see that you will not use the p chi-square q function because I found another function that is much more straightforward to run the test. But this is important to watch because then you know what the function is doing on the background, so you're better equipped to interpret the findings of a chi-square test. Anyways, two hypotheses, nothing is going on. Race and death sentence are independent. And the alternative hypothesis that something is going on, some relationship there between race and death sentence is present. And because the probability of seeing the deviation that we saw with 1 degree of freedom is less than 0.05, we're going to reject the null in favor of the alternative hypothesis. And the interpretation here is that there is evidence that death penalty is related to race. And the descriptive statistics show, which is the contingency table shows, the one that we just looked at, shows that non-white individuals receive the death penalty more frequently than would be expected by chance, while the opposite is true of white individuals. So I want to say this one more time because it is important. The fact that the p-value is at less than 0.05 just tells us that there is a relationship between race and the decision for the death penalty. To determine which race is actually being privileged and which race is being biased again, which race is receiving more death penalty than expected, is suffering from that relationship, we need to look at the contingency table. We need to look at the relationships between the observed and expected counts. What we're seeing here is that more individuals from other races other than white, are receiving the death penalty than would be expected if their race had nothing to do with the decision for the death sentence. And to the contrary, less whites are receiving the decision for the death penalty than would be expected if the decision for the death sentence had nothing to do with the person's race. So there is a bias against individuals of other races that are not white in our jury system. All right. So now let's watch some, we'll stop. This is it for lecture. And now we're going to go on and work on the guided activity in the lab, which I'll walk you through together. All right. See you there.